I grew up in a pretty conservative environment, and Star Wars was like borderline.
Seriously?
It's like Star Wars is borderline because what is the Force really? Is that magic? Because that shit is not okay. That's the kind of environment I grew up in. I'm sure that like kind of makes sense though. So, okay. So we are on chapter 3 now. Woohoo! Measurement systems as dynamic systems. So, measurement systems respond to the quantities measured. This response is crucial to our interpretation of a measurement reading. For instance, a thermometer does not give instantaneous measurement. Rather, we wait for the response to settle before taking a reading. However, time delay is only one way in which the measurement system response affects the reading. More complicated effects require further analysis. So, like, you're taking your temperature, the thermometer, and like you gotta wait a minute, right? But you're always trying to sneak a peek. What is it? Do I have a fever? That kind of thing. So we're
hoping for that fever so you don't have to come to class.
Yeah. Back when you had to go to school, it was like, oh man, I hope I have that fever. I would really like to not go to school. Now it's like, oh, I paid those administrators a lot of money for this class. I probably should go. Yeah, it's just going to be like blank and then ha ha ha, we're all laughing. Oh, man. No, I'm not going to edit it because I'm a revolutionary. So
Man, you're gonna get 1,000 subscribers a day if you post that video.
Right? Yeah, I just don't see me going viral. I just don't think it's gonna be a thing. But like for the wrong reason, like for something that I didn't mean to do, like I could see that happening. Like, university professor says dumbest thing ever in front of class, and it's like on YouTube and it becomes like the new Rickrolling. Yeah.
At the end of all your lectures, you should be like, if you enjoyed, please like and subscribe.
Yes. I put out new videos every week.
Smash that like button, guys.
Oh yes. And like put the little like arrow to it. Yeah. Okay. All right. So pretty much measurement systems respond dynamically to the quantities that we're trying to measure. So we kind of need to understand that in order to do measurements well, is the idea behind this chapter. So, like a delay is something that's pretty easy to understand, like you gotta wait for your reading, but there are more complex interactions that the system has, so you have to understand system dynamics a little bit, at least. So it's a field devoted to such system analysis by representing systems with mathematical models. Specifically, we will consider lumped parameter models of measurement systems. These models give insight into the measurement system's behavior and allow us to properly design measurement systems and interpret their readings. Modeling does not replace calibration, but complements it. So we're still going to need to calibrate our systems. We're not going to be able to say, oh, here's a mathematical model for how a strain gauge works or something, and here's how an amplifier works. So we don't need to worry about actually measuring this stuff. We just have a model and go forth. It's not, it doesn't quite work that way. You still have to calibrate, but in order to design your measurement system, you have to have a pretty good idea of how it's going to respond. And that's what we're going to look into. So that is the beginning of the introduction. I'm going to move myself around here a little bit. And we'll open up the first lecture, which is, I think, just good, clean fun. And don't tell the others, but if you're taking this class from me, it's probably going to be a little easier easier for you in system dynamics because you will have gotten a little bit of a head start in systems. So I don't know how Dr. Einstein is presenting it. Maybe he's doing it. I mean, our chapter 3 in our textbook is also on this. I just felt like we could add a little bit of nuance to what they do. They present pretty similar stuff, but I'm going to do it in a little different way than they do, so it gives you a different view of it. But I still think reading the textbook is going to help you with an understanding of exactly what we're doing here too in chapter 3. So this lecture is on dynamic system representations. So dynamic systems, measurement and otherwise, have several representations, mostly graphical or mathematical. For instance, schematics, linear graphs, which we haven't talked about, but we will talk about in mechatronics, and block diagrams are graphical representations. The foci of this lecture are three, you like that? It's plural for focus. The foci, you like that? The foci of I had to Google it to double check, I was pretty sure, but I was like, I don't want to put this on YouTube if I'm not sure that it's foci. Okay, so the foci of this lecture are 3 mathematical representations and a graphical representation. So we're going to start, I'll list the 3 mathematical and the one with the graphical. So the 3 mathematical ones are the input-output linear ordinary differential equation, which you guys all know how to do. In mechatronics, we've been solving them, so that's one representation. Second one is the transfer function. So we're going to learn about the transfer function. Very useful, very ubiquitous. A lot of engineering analysis happens through transfer functions. So we'll get introduced to them a semester early. System dynamics is when others might get introduced to. 3, the frequency response function, which is related to the transfer function. And also very useful, especially for spectral analysis. And then finally, the block diagram I'm going to introduce in this lecture as well, which is another way to represent systems, but graphically. Different than the schematic or the linear graph. All really useful concepts and will be useful, especially, it's kind of like the minimum grouping of representations that I could use for measurements. So refer to 3.1 for an illustration of the relations among system representations. So this is this pretty figure. And it's a little intimidating, possibly, but it's also hopefully like a map. It's like if you look at a map, like there's a lot on there, but you can like slowly work your way around, become familiar with it. So the thing to recognize first off is that these are representations of systems, of dynamic systems. So this top 3, this little triangle up here, these top 3 are all graphical representations. And then these bottom 5 are mathematical representations. And they're all useful for different analytical techniques. And we're going to learn how to use all of them over the course of this year, if you include system dynamics in there. In this class, we're going to focus on just actually a pretty small subset of them, but I wanted to show you where we are in relation to the others, and hopefully that'll give you a better feel for the terrain that we're working in. So let's talk for just a moment about the schematic, okay? So we've seen the schematic, right? Like a circuit diagram. We've been working with a lot in mechatronics. In dynamics, you probably saw some mechanical schematics where you have masses and springs that are drawn on things. Like it doesn't necessarily look like the physical situation exactly, but it gets like kind of like the minimal elements in there to convey how things work, right? So that's what a schematic's doing for you. So usually those schematics are for lumped parameter modeling, and we've talked about that in mechatronics before, where you say, oh, okay, there's all this stuff going on. We're going to say that's like a mass, and this is like a spring, and et cetera. So that's what the schematic is for. Now, we almost always start with the schematic, no matter what system we're working with, dynamic system. So we're going to start with the schematic, and then two alternate representations can be the linear graph and the block diagram. We're going to talk more about the block diagram later in this section, but just so you know, that's where we're headed. So schematic, yes, we'll be working with those. Block diagram, we will be working with those as well. And then down here, we have all the mathematical representations. So what you've done in mechatronics is take a schematic and write it as an input-output differential equation, right? So you would write like this differential equation. This is like a little first-order example. Single input, single output system, and you can solve for the response and do all kinds of things. So that's a dynamic system representation. That's mathematical. It's like the first one that you learn is the differential equation form. And we can solve those, and we can do lots of great stuff with them. There are also others. So in this class, we're going to learn how to do, actually in this lecture, how to go from a differential equation to a transfer function, and to go from a transfer function to a frequency response function, which they're all related. And it's actually not that, once you see the process of converting among them, the process isn't too bad. These ones are actually especially pretty straightforward. So we'll learn how to do these two at the bottom row, the transfer function, the frequency response function, and the input-output differential equation we'll also learn. So that's what we're mostly gonna be working on the right side of this. So schematics, block diagrams, input-output differential equations, system transfer functions, frequency response functions. Over here, we'll be working in mechatronics with linear graphs and state space models, and we'll learn how to convert those. There are ways to go among all of these different representations. So learn how to convert those to state space models, and then those into other representations as well. So that'll be in mechatronics and system dynamics. We'll be working over here in this class. Kind of two approaches, and they're useful. All these representations have their sort of use cases when they're like really helpful. So that is what you spend most of your time doing in system dynamics related courses, is coming up with these different models and then using them to do analysis. So once you have these models, if you have like a state space model or you have a transfer function, you can plug those right into MATLAB, for instance, and you can start simulating like immediately. Takes 5 minutes. So they're very powerful, these representations. You can start getting simulation results immediately, see how the system would respond to some input. It's pretty cool stuff. And then you can do other techniques of analysis as well, like how is the system going to behave in a given situation? Are there any resonances? That type of thing. So lots to learn about on those fronts. Okay, so back over here. So the first representation we're going to learn about is the input-output ordinary differential equation, which we already know about. So consider a dynamic system described by the input-output differential equation with independent variable y of t called the output, dependent variable time t, input u of t, constant coefficients a and b with different subscripts, order n, and m less than equal to n for positive or non-negative integers. So all the maths, but essentially this is an nth order linear ordinary differential equation, right? It's written in this like kind of scary looking form, but essentially this is the same thing as writing, if it was a first order equation, this would just be tau y dot plus y equals u, right? Like this is just like the most general case. So this might describe, for instance, the output voltage reading from an input force on a piezoelectric transducer. Mechanical, electronic, thermal, fluidic, and many other types of dynamic systems can be described with this equation. It is important to note that this describes only linear, single input, single output systems, meaning you can only have one input and you can only have one output. We'll learn that one of the reasons why we have this state space representation is that we can do multiple inputs and multiple outputs with it. Whereas this is more limited. But in fact, many of our systems are single input, single output. And I would say most of our measurement systems are single input, single output, and approximately linear, at least in some operating regimes. So, I mean, realistically, nothing is super linear. Well, very few things are super linear. But in some operating regime that we care about, they're pretty linear. We can approximate their behavior. Okay. So that is this. We already got one of the three math ones done, and we already knew it. It was already familiar. The next one we're going to need the Laplace transform for. It's called transfer functions. The Laplace transform of equation 3.1. So if you took the Laplace transform of this input-output ODE, it yields something interesting, assuming zero initial conditions. So do y'all remember how to take the Laplace transform of something? Well, I assume you do remember. Oh, geez. I didn't transfer the right thing to my notes. I'm going blind. Or that doesn't sound right. I'm flying blind. That's what I was trying to say. I'm flying blind. Yeah. So the Laplace transform,
So you're winging it.
I'm winging it. Always with the flying analogies, though.
Yeah.
It's interesting, huh? You take the Laplace transform, and I'm going to try to not use the squiggle brackets because they kind of bug me. But Laplace transform of the left-hand side, which was, go back over here, annoyingly 2 pages, which was this. And then we take the Laplace transform of the right-hand side. They have to be equal to each other, right? Well, we're going to do it. It looks a little hard and scary, but it's not too bad. All right, so dn, so the nth derivative of y with respect to time plus a n minus 1, the n minus 1th, n minus 1st, I'm not really sure, derivative, oh, this should be to the n, n minus 1, plus, so descending in order to a1 y, no, a1 dy dt, plus a0 y. Whew. So Laplace transform of all that on the left-hand side, so-called left-hand side because we're putting it below, divided by the Laplace transform of b subscript m, coefficient, d m u dt m.
Dr. Quinn, did you mean to forget the a sub n in front of
You know, it seems like it, but in fact, you can always, it's just sort of conventional that we just divide both sides of the equation by whatever an is.
Hence we have the an minus 1.
So yeah, so everything else needs to have a coefficient to be completely general, but we can always make one of the coefficients 1. And just by convention, we chose that one. So yeah, so an, we could have an an in there, but
It's arbitrary.
yeah, we have chosen to always just divide through by whatever is there, and we have just 1 as that coefficient. But thanks for checking, because that is exactly the type of thing I would forget to write down. Bm minus 1, m minus 1 u dt m minus 1 plus all the way down to b1 du dt plus b0 u. Whew. Done. Okay? So that Laplace transform is an integral, right? And remember, like, the basic properties of integrals and Laplace transforms. One of them is that when you have a summation inside, you can distribute your summation or your Laplace transform to each term in the sum. So, and also constants can come out. Just like with an integral, you can pull a constant out of the Laplace transform. So let's rewrite that as being, so the left-hand side is going to be the Laplace transform of d n y dt n plus, oh, that's the end of the Laplace transform, plus a n minus 1 times the Laplace transform of d n minus 1 y dt n minus 1 plus all the way down to a1 Laplace transform of dy dt and plus a0 Laplace transform. Oh crap, I switched over to squiggles. I knew I was going to do it because it's just like second nature to do the squiggles. It's never been explained to me why people use squiggles for Laplace transform and for Fourier transform. And so I'm bucking the trend. I'm going to use parentheses. Viva la revolution. Okay, so on this side we have bm Laplace transform of dm u d t, that's a u, t m plus b m minus 1 Laplace transform of d to the m minus 1 u d t m minus 1 plus all the way down to b1 Laplace transform of du dt plus b0 Laplace transform of u, and that's the end of it. Whew. Okay. Dear Lord is right. So we now have these Laplace transforms of mostly just time derivatives, right? Do y'all remember what the Laplace transform of dy dt is, for instance?
From 0 to infinity of
Yeah, so the definition is that.
power of negative st dt Laplace transform, which is in terms of s.
You're right, but fortunately we have had people come before us who have determined that the Laplace transform of the nth derivative of y with respect to t is just s to the n times y, the Laplace transform of y. Okay, so it's a property of it. It's essentially a result of the integral nature of Laplace transforms, the definition of it. You can go back to that definition. I'm not going to derive it. It was a nice result, and when we say we don't worry about the initial conditions, this is where it comes in real handy because there are also some initial conditions in that formula. We don't want to mess with those. So, and to derive the transfer function, which is what we're trying to do, we don't need them. So we have on the left-hand side, so on the left-hand side we have s to the n, the Laplace transform of y, I'm going to just write as y of s, capital Y of s, plus a n minus 1 s to the n minus 1 y of s, plus all the way down to a 1 s y plus a 0, and the Laplace transform of y, we're just calling, oh man, I wrote a lowercase y, didn't I? Wrong y.
Oh no. Then y of s.
Yeah, it's y of s. Okay, good. So that's the left-hand side. The right-hand side is bm. We're getting a little better, right? Bm s to the m. Our fingers are starting to hurt, but they're okay. Y, or not y. Now we're doing the Laplace transform of u's, right? U of s plus bm minus 1 s to the m minus 1 u of s plus b1 s u of s plus b0 u of s. So we'll factor. We'll do one more step. We'll factor out y and u on each side. Okay? So we're left with s to the n plus a n minus 1 s to the n minus 1 plus all the way down to a 1 s to the 1 plus, we're factoring out the y here, plus a 0. All of that on the left-hand side is times y of s, right? Every term in this row here has a y of s in it, so we factored it out. Similarly, on the right-hand side, every term has a u of s, so we can factor it out. So we could say equals, I'm gonna have to plug in after this, equals b m s to the m plus bm minus 1 s to the m minus 1 plus b1 s plus b0 times u of s. Okay, getting close. Solving for y, then.
Before we solve for y,
Ah,
I have a question.
yes, what is your question?
So in the so-called right-hand side
Yes.
of the equation, we start off that series of, or that set of individual terms with bm as compared to the left-hand side where we just set in an arbitrary 1.
Yes.
Why did we do that? I might have missed that. Is that something I just take?
We could have, we can choose one or the other to be 1. We can choose any one of these to be 1 by dividing both sides of the equation by whatever it is, right?
Correct.
So we chose
The left-hand side.
the left-hand side's first term to be 1, just by convention. That's just what people do.
But then the right-hand side has to have that term in front of it.
It has to have that term because you can only make one of them guaranteed to be 1. Because if you divided it through both sides by bm, then this one over here would be 1 over bm, and it wouldn't be 1 anymore. So,
Okay.
yeah,
Thank you.
that was a well-timed question. I managed to get my laptop plugged in. It was great. Nice work.
Timing is everything.
That's right. We're on. It's good. This is good. This is good. Okay, so let's solve for y. So we're pretty close. We've got y factored out here, so there's only just need to divide through by this polynomial in s. So we get that y of s equals, it's a fraction of polynomials, right? So y of s equals bm s to the m plus bm minus 1 s to the m minus 1 plus b1 s plus b0, all of that divided by s to the n plus a n minus 1, s to the n minus 1 plus a1 s plus a0. All of that is multiplied by u of s. Whew. Okay.
Yes. Awesome.
Hooray! Did we mess up? Oh yeah, you're a step ahead. We're not quite there. So we solve.
Summation.
We could write them as a summation too. That
A lot less writing.
it would be a lot less writing. You're right. For some reason, this is how we always do it in engineering. For some reason, we write out these polynomials. I do agree. Summation notation is a lot nicer, but there are a lot of folks who get really scared of it too. And they're like, I see a summation and I don't know what's inside of it. It's scary. So we got to take that into account. In any case, our fingers hurt, but our souls are full of happiness. So the inverse Laplace transform of y is the steady state solution. Right? Like by definition, y of t equals the inverse Laplace transform of y of s. So that's nice. I mean, it's essentially solving this equation using Laplace transforms, which the input-output differential equation, you did that in your differential equations class. That was what you learned Laplace transforms to do, was to potentially do this process. However, this is not our primary concern. Rather, we are interested to define the transfer function, h of s, as the ratio of the output transform y of s to the input transform u of s. In other words, h is defined as y over u, and I helped us out there by rewriting it for us. It's essentially just this fraction here. And not just essentially, it is that fraction.
H of s.
That's h of s. That's the transfer function. That's all it is. So like, that object, I mean, it kind of seems scary, but like at the same time, it's just a fraction of these two polynomials that came from our input-output differential equation. Yeah. But mostly we're working with small, like in this class, we're mostly working with first and second order systems. So usually this degree is like s squared is the biggest one you're going to see. Maybe like an s cubed.
So is that fraction equal to h of s? Or is
Yeah.
it just the denominator?
The whole thing, the whole fraction.
So the converted form would then be y of s is equal to h of s times u of s?
Yes. So this right here implies that y equals hu. I drop the of s in notation sometimes because I think it's a little clearer, a little easier to see. We'll see why we use the of s incessantly in a moment. Okay, the transfer function is exceedingly useful in many types of analysis. One of its most powerful aspects is that it gives us access to thinking about single input, single output systems as operating on an input u and yielding an output y. In fact, this is the foundation of another graphical technique called block diagrams. And what do you know? We're in that section now. Block diagrams. What?
Nice transition.
I know, right? I set that one up, didn't I? In fact, I originally had it as part of the same section, and I was like, could just put another little subsection in here. Called block diagrams. All right, block diagrams, also called operational block diagrams, if you're Rowell or Wormley, represent inter- and intra-system relationships. So relationships, dynamic system relationships inside a system, that would be intra, and out among systems is inter. Okay? A block, shown in figure 3.2, represents a dynamic system with input U, output Y, and typically transfer function H of S. So that's right here. Input U, output Y, transfer function H. This is the block of the block diagram. Okay. This is we think of transfer functions as taking in inputs, operating on them, and then spitting out outputs. And that's what this says. Y is equal to HU. Sometimes we also use a common transfer function letter is also F. But I left it out on this one. I chose H in this case. You're welcome. Okay. So, each block can be considered in the Laplace domain to multiply its input by the transfer function, as illustrated in 3.3 left. So, if we were to look at this, the input is multiplied by the output. So we can concatenate these things. So if I was to call this, like, I don't know, W, then W would be equal to GU multiplication. Y is equal to HW. And so we plug this W into that W, and we get GHU. Which is that. So you can just, like, if you have blocks that are next to each other, you just smash them together. They're concatenated. You don't always want to, because you might want to know what comes out of one block and whatnot, but effectively, you can just mash them together, multiply them in the Laplace domain. Also shown, oh yeah.
This is like just a kind of random question. Is this kind of similar to LU decomposition? Like in that same way, like you can use one to get the other. Not really a matrix.
In a sense, yes, but I wouldn't say I wouldn't say like in a functional sense it's the same. Like, I see the analogy that you're kind of pointing to, but I wouldn't take it too far, I guess. I think this is kind of similar, but yeah. It's kind of like if you thought of a matrix as an operator, like if this was the A matrix and this was the B matrix, then you would think of A acting on U, and then B acting on AU, and Y would be equal to that. So I see the analogy, but I wouldn't take it too far. Like, because these are not matrices. I mean, they could be if it was a zeroth order system. We haven't defined that yet, but yeah. Anyways. Okay, let's, or no, yeah, okay. These are all just polynomials in S right now. Good, so, oh yeah, and then also shown in figure 3.3 on the right is the summation block or junction that adds or subtracts its inputs. So you could have this is the summation junction, where you take in U1, you take in U2. Depending on the sign that is next to the arrow as it comes into the block, you either add that term or subtract that term. So U1 came in with a plus sign, so it's added. U2 came in with a negative sign, so it's subtracted. So we can represent these algebraic relationships like GHU and U1 minus U2 in this graphical way, and it's really useful. It's used very frequently. And this is the last thing that we'll cover today, and I'll let you go. Block diagrams differ fundamentally from circuit diagrams and linear graphs in that they do not load each other. Okay? That is, concatenating two systems does not affect the operation of the first. However, since we can write an input-output differential equation for a circuit, and we can write a transfer function for a differential equation, block diagrams can represent a circuit or many other dynamic systems. We must be careful to make sure that subsequent connections do not load the output of another block. Once we write them as transfer functions and we write them in this form, we're making that assumption that they don't load each other. That is, blocks have infinite input impedance. So a measurement device that has effectively infinite input impedance is the multimeter, right? If you connect a multimeter up to the circuit, you're saying, well, it's hopefully not going to load the circuit, because if it does, it's going to affect the measurement they're trying to make. So you want each block to not load what its previous block is. So the other block can just operate however it was going to operate before you connected it.
Looks like a flowchart.
Yeah, it's very much like a flowchart.
Flowchart.
It's also used in computer science for talking about where a signal flows or a data stream flows. It's really useful. It's used a lot in engineering, especially in controls and system dynamics. So they're pretty intuitive, but it is important to recognize, like, if this paragraph was kind of like tripping you out a little bit, it's okay. Most people find block diagrams to be pretty intuitive, and you're almost never going to have to worry about this. But it's important to just say this at the beginning. You got to be careful. Yes?
Can you give a little insight on the homework assignment?
Oh, I thought you would never ask.